What you're seeing right now isn't a game engine like Unity or Unreal. This is raw geometry rendered in a browser using nothing but vanilla JavaScript. Notice how the shadows wrap perfectly around the corners, stretching and shrinking in real time. This is the foundation of digital sight. In Among Us, the most dangerous thing isn't the imposter, it's what you can't see. The game uses a fog of war mechanic where your vision is physically blocked by the walls of the ship. But how does a 2D game calculate sight in real time? How does it know exactly where a shadow would start? It's a technique called raycasting. Long before we had modern 3D graphics, games used this exact logic to fake a 3D world by shooting rays out from the player's eyes. Hi everyone, I'm Amlan Pati. We have mastered movement, gravity, and connectivity. Today we are giving our engine eyes. We are going to solve the geometry of line-line interaction to build a dynamic shadow system from scratch. Let's get into it. Raycasting is just a fancy term for a single geometric question. Where do two lines cross? Imagine our light source is at point P. We shoot a ray toward point mouse. At the same time, we have a wall defined between point Q and Qn. To find the hit, we represent both as linear equations. We are looking for two specific values, T and U. T represents the distance along our ray. If T is 0, we're at the start. If T is 1, we have reached our destination. U represents where on the wall the hit happened. The math is simple but strict. If T is between 0 and 1, the wall is within our reach. If U is between 0 and 1, we actually hit the segment of the wall and didn't just fly past it in infinite space. This logic is the collision detector for our light. Just like in our previous videos, everything starts with the canvas. This is our entire world, a blank digital space where all the geometry lives. Setting up, we want a dark environment, so we'll set the background to a deep black. We want the mouse to feel like a flashlight. Game engines don't start with characters or lighting. They start with coordinate systems, shapes, and math. Our worlds are stored as a simple array of coordinate pairs. Think of these as the obstacles in our world. In a real game engine, these would be generated by your label data, but here we'll hardcode a few segments to test our math. The mouse will act as our light direction. Wherever the mouse goes, that's where our ray will point. So instead of a character holding a flashlight, we are just using the mouse as the source of vision. Now, for the brain of our engine, the get intersection function. It takes 4 points, the start and end of our ray and the start and end of our wall. The first thing we calculate is the denominator. If this is 0, it means the lines are perfectly parallel, they will never meet. If it's not 0, we solve for T and U. T tells us how far along the ray the collision happens. U tells us where along the wall that collision happens. If they both fall within the 0 to 1 range, we return the exact x and y coordinates of the collision. It ensures that the collision happens within the visible parts of the lines. Without this check, we detect intersection out in infinite space, which would completely break the illusion of solid walls. Now, we bring everything together inside the animation loop. This loop is like the heartbeat of the engine. Every frame, we clear the screen, run the math, and draw the result. First, we draw the walls themselves. These are the solid objects in our world. Visually, they're just white lines, but mathematically, they're collision boundaries. For each wall, we run our intersection test. So the ray is basically asking every wall, do I hit you? And if I do, how far away are you? This happens every single frame, and in real engines, this can happen thousands of times per second. Now we draw the ray itself. If there's a collision, the ray stops exactly at that point. If there isn't, it just continues all the way to the mouth. So visually, it looks like light being blocked by the wall. And this red dot marks the exact collision point. This is the precise pixel where the ray meets the wall. It's not an approximation, it's a mathematically exact solution. The version we built today shoots rays at fixed angles, but if you look at the advanced version on my GitHub, I use a technique called vertex casting. Instead of shooting 360 rays, it only shoots rays towards the corners of the walls. It's faster, sharper, and it's how professional 2D games handle complex lighting without lagging the CPU. We have given our engine eyes. You now understand the geometry behind fog of war and 2D shadows. In the final video of this series, we tackle the final boss of 2D physics, elastic collisions and conservation of momentum. Like, share and subscribe, and I'll see you in the next one.